our problem tells us that when 1.125 grams of a liquid hydrocarbon, CXHY, so we don't know how many C's and H's they are, so it's a mystery liquid hydrocarbon, was burned in an apparatus like that shown in figure 4.7. This is the apparatus. This is our mystery hydrocarbon getting burned, or it's combusting with oxygen. You need oxygen for the combustion to occur. So when it burns in this apparatus, and it burns with oxygen, it tells us, and we have 1.125 of it to start with, it tells us that 3.447 grams of carbon dioxide and 1.647 grams of water were produced. So let me write that reaction right there. So let me just write this first sentence right here. Write all of the information that they're giving us. In that first sentence. They're saying that when we start off with that liquid hydrocarbon that has X C's and Y H's in it, and it's in its liquid state, they say it's a liquid hydrocarbon, and when we combust it using oxygen in its gaseous state, we will produce carbon dioxide. And water. And you can't even realistically balance this equation because you don't know how many carbons and hydrogens you have on the left-hand side. But what they do tell us is how many grams of everything, of at least this we start with, and how many of the grams of each of these we end up with. And we're assuming that we have an excess of oxygen, that this hydrocarbon is the limiting reactant. We just have an abundance of oxygen, just enough oxygen to turn all of this hydrocarbon, to combust all of it into carbon dioxide and water. And they tell us that we have 1.125 grams of the mystery substance, and then it produces 3.447 grams of carbon dioxide and 1.647 grams of water. Now, to solve this, well, let me finish reading the problem. They tell us in a separate reaction, or in a separate experiment, the molar mass of the compound was found to be 86.2 grams per mole. So I'll write that down here. So CXHY molar mass is equal to, let me write it this way instead, just to go with the convention that I've been doing. We have 86.2 grams of our mystery substance, CXHY, per mole of our mystery substance, CXHY. And then they're asking us in this problem, they say, determine the empirical and molecular formulas for the unknown hydrocarbon CXHY. Just as a refresher, empirical means just the simplest whole number ratio of the atoms in our molecule. So the simplest ratio of our carbons to hydrogens or hydrogens to carbons will give us the empirical formula. The molecular formula is exactly how many carbons and hydrogens do we have in each atom. And I suspect we're going to be able to use this information to come up. Once we have the empirical formula, we then can use this molar mass right here to figure out the actual molecular formula. But let's figure out the empirical formula first. And the way we can do it is we can say, well, gee, how many moles of carbon dioxide do we get produced? How many moles of hydrogen? And then we can say, well, in the final product, how many moles of carbon do we have then? And how many moles of hydrogen then do we have there? And then we can figure out the ratio. And the ratio of carbons to hydrogens or hydrogens to carbons in the product, that's going to have to be the same as the ratio in the reactants. And they all came from this reactant right there. They didn't come from the water. And then hopefully we'll be able to figure out what kind of the simplest whole number ratio of hydrogens to carbons or carbons to hydrogen is. That sounds very complicated, I think, but I think if we take it step by step, it won't be too bad. So a good place to start, let's figure out how many moles of each of these substances we have. I'll start off with the carbon dioxide. So if I start off with the carbon dioxide, what is the molar mass of carbon dioxide? So its atomic weight, carbon is 12 plus, you have 2 oxygen, so 2 times the atomic weight of oxygen is 16. You could look that up if you like. But that's equal to 44 atomic mass units. That's its atomic weight, which is, the weighted average of all of the isotopes and all of that business. But if you have a whole mole of carbon dioxide, 6.022 times 10 to the 23rd of these molecules, then you're going to have 44 grams of the substance. So we have 44 grams of CO2 per mole of CO2. And if we want to figure out how many moles we have with us, we know that we're starting off with 3.447 grams of CO2. And we want to multiply this up by something that has grams of CO2 in the denominator. So we want to multiply it by something that looks like this. And we want to turn it into moles of CO2. So it should have moles of CO2 over grams of CO2. Well, that's the inverse of this right here. This is grams per mole. We want moles per gram. So if instead of 44 grams per mole, we have 1 over 44 moles per gram. Or for every 44 grams, we have 1 mole. For every 1 mole, we have 44 grams. I just inverted this. So let's multiply. The grams of CO2 cancel out with the grams of CO2. And you are left with 3.447 divided by 44. So let's figure out what that is. So you have 3.447 divided by 44, which is equal to 0.07834. So 7834. Let me remember that. So that is 0.07834 moles of CO2. That's our only units left. Moles of CO2. Now let's figure out how many moles of water we have. So I can do the exact same thing over, let's see, where should I do that? Let me write it over here. So let's do the water in orange right here. So we're starting off with 1.647 grams of H2O. And what is water's molar mass? Same argument. Its atomic mass is, each hydrogen is 1, but you have 2 of them, so it's 2 times 1 plus 16, which is the atomic weight of oxygen. So 2 times 1 plus 16 is 18. That's also its molar mass. So you could say 18 grams of H2O per mole of H2O. Now, to convert the amount of grams we have, to moles, what we want to do is multiply it by something that has moles in the numerator and grams in the denominator. We want grams of H2O in the denominator and moles of H2O in the numerator. And that's the exact inverse of this. So if we have 18 grams per mole, we have 1 over 18 moles per gram. And what is this going to be equal to? So this cancels out with that. So we're left with 1.647 divided by 18 moles of H2O. Let me scroll over a little bit and get the calculator out. Clear it out. And so we have 1.647 divided by 18, which is 0.0915. So let me do this in a new color. We have 0.0915 moles of H2O. So far we figured out in our products how many moles of carbon dioxide we have and how many moles of water. Now, I said we want to figure out the ratio of hydrogens to carbons or carbons to hydrogens to figure out the empirical formula right here. And to do that, we can say, hey, look, all of the carbons and the hydrogens in our products, they all had to come from our mystery hydrocarbon. So if we can figure out the ratio of hydrogens to carbons in our products, we'll know the ratio of hydrogens to carbons in our reactants, because they all had to come from this guy right here. The oxygen obviously had no hydrogens and carbons in it. So all of these hydrogens and carbons came from our mystery substance. So how many moles of carbon do we have? how many moles of carbon do we have in the carbon dioxide, or in our products? Well, the only product with carbon dioxide, the only product with carbon is the carbon dioxide. This has no carbon in it. So if we have this many carbon dioxides, we also have the same number of carbon atoms. The same number of carbon atoms, moles of atomic carbon. And you might say, hey, wait, a mole, that's just a number. This is saying 0.07 times, 6.022 times 10 to the 23rd times that huge number. A mole is just a number. Very important to remember. So this means we have the same number of carbons. And if we have that many waters, how many hydrogens do we have? Well, for every water molecule, we have 2 hydrogens. So we're going to have twice as many hydrogen atoms. So let's multiply that times 2. So times 2 is equal to 0.183. 0.183. So we have 0.183. I could even put a trailing 0 because we actually had, well, I think I lost a significant digit here. I could have put a 0 right there. But anyway, I don't worry too much about that. 0.183 moles of atomic hydrogen. Because for every water molecule, we have 2 hydrogens. So I just took this number and multiplied by 2. And now let's figure out the ratio of hydrogens to carbons. And that's pretty easy. We just take the ratio of that to that. So the ratio of hydrogens to carbons is 0.183 moles of hydrogen in our product for every 0.07834 moles of carbon in our product. And somehow we have to make this into some type of a whole number ratio. Let's see whether we can do anything here. Let's just divide this right here and see what we get. So if we just take, well, we have the 0.183 there, so let's divide it by 0.07834, and you get 2.336. So this is approximately equal to, I'll do a new color, is approximately equal to 2.336 moles of hydrogen for every 1 mole of carbon. And this doesn't look like that neat of a ratio, but this is pretty close to 1/3. So maybe if we multiply the numerator and the denominator by 1/3, by 3, what do we get? Well, 3 times 2 is 6, and 3 times 1/3 is another 1. So this will be 7 moles of hydrogen. I'm approximating it. I'm trying to get to some reasonable whole number. 7 moles of hydrogen for every 3 moles of carbon. And this was a little bit of an art to it. I said, okay, 2.33 to 1 or 2.336 to 1. Well, gee, it just looks like over here, this part of it, looks like if we multiplied that by 3, we're going to get pretty close to a whole number. So let me multiply the numerator and the denominator by 3. That's kind of the art there, to recognize what do you have to multiply this to turn it into a whole number. And if you don't believe me, we could take that number and multiply it by 3. And you get something very, 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 very close to 7. So that's enough for me. So you multiply them both by 3, you get 7 moles of hydrogen for every 3 moles of carbon. And we've figured out our empirical formula. We have 7 hydrogens for every 3 carbons. Right? If we have 7 moles for every 3 moles, that means we have 7 hydrogens for every 3 carbons. And so the empirical formula of our mystery hydrocarbon, so empirical formula is for every 3 carbons we have 7 hydrogens. Now, the next thing we want to figure out is the exact molecular formula, the exact number of, this is just the minimum ratio, but maybe we have, 9 carbons for every 21 hydrogens. We don't know. So let's use the other information they gave us in the problem, where they told us that the molar mass is 86.2 grams per mole. This information right here. This information right here. Let me copy that. 86.2. That looks like an 80, but we'll remember it says 86.2. So let me paste it over here. That's what they gave us in the problem. So just for kicks, what would be the molar mass if this was the molecular formula? So as it's written right now, well, there's a couple of ways. We could do it algebraically and all of that, but the simplest way is to say, as it's written right now, what would be the molecular mass of this? Well, it would be, or the molar mass, I should say. So it would be 3 times 12 plus 7 times 1. 3 times 12 is 36, plus 7 is equal to 43. So if this was the molecular formula, its molecular mass would be 43 grams per mole. But they tell us in the problem that the molecular mass is 86 grams per mole. So they're saying that the mass is twice as much as this. We must have twice as many atoms in the same ratio. So the molecular formula for this, we're in the home stretch now. The molecular formula must have twice as many atoms in the exact same ratios. So it must be C3H7 times 2, or we could write that as C6H14. So we have, this is still a ratio of 14 to 6, which is 7 to 3. But using this information, we were able to figure out the exact number of carbons and the exact number of hydrogens in this molecule. Anyway, hopefully you found that fun.